Our last speaker before the break is Quincey Koziol from NVIDIA. Hey, Quincey.
Hey, Scott. Let me get this set up here. PowerPoint and Zoom arguing about the screen. Okay. Yes. That's there.
Did you see share?
Okay, so this is a design overview. I'm not going to get into like, here's how we're going to change the callback interface directly, right? I don't need to, in 20 minutes, I cannot possibly cover the details that we need to cover for moving HDF5 down into an accelerator-native framework that that will operate on today's GPUs, right? This is where kind of where we need to go, right? The modern I'm sorry, I jumped right in. My name is Quincey Koziol. I'm a principal engineer with NVIDIA. I've been working on HDF5 forever. So this is my take on how we need to modernize HDF5 to bring it into the accelerated computing era, right? So Jensen, next slide. Why are we not going to the next slide, guys? Thanks. Jensen makes this case, right? And it's really obvious that the world is moving into accelerated computing, GPU computing, if you like. It can be a very, very, very powerful way to go forward in all ways of doing computing. Obviously, we're playing into the AI realm right now, but it's got tremendous impact everywhere, right? In a lot of ways. The world is moving away from general purpose CPUs and to some degree investing heavily in GPUs and other accelerated computing. So you all know this, but this is the principle, like, hey, it's a data set, right? And it's either big picture, there are special cases, I wrote them. But what we're going to talk about today is like contiguous storage for data sets and chunked with compression for data sets, right? There are important other use cases, virtual data sets and compact and lots of external storage and all kinds of goodness. But today, just to get the big picture on the ground in 20 minutes, what I'm planning to do is mainly focus on how this is going to affect the contiguous and chunk data sets in the I/O pipeline for HDF5. Everything else is pretty straightforwardly applicable. And I'm also going to talk primarily about serial I/O. Because that's the majority case for these kind of compute. Yes, MPI is important. Yes, we will figure out how to do it well, but it has some additional interesting complexity that's going to have to need some layers of design that just aren't able to fit into these kind of slides. Not yet. So this is a cartoon drawing, right, of a GPU node, right? We've got a host CPU with some memory, a GPU or more GPUs on a node in your rack or wherever, connected together with something like PCIe, and ideally that attaches directly into some storage location on that node. It could hypothetically be, a remote-ish parallel file system like Lustre or something else, but it at least has a driver that's sitting on the interconnect, right? So it's fast. It's not way off the Ethernet or something funny. So this is kind of going to be our big picture for working through why we have a problem today. Because today, all the I/O in HDF5, modulus in special cases, but principally we're making POSIX calls. Even if it goes through MPI, it's eventually a POSIX call. The dataset chunks are in the CPU memory, not the GPU memory. The I/O filters today are running on the CPU, and they're accessing those chunks in the CPU memory. And then finally, when we get all this done, right, we transfer the data over to the GPU. So what this kind of looks like is GPU says, hey, man, I need some more data. So CPU gets busy, right? It says, okay, I will start fetching in some data from storage. It comes in, it's, let's say, compressed chunks, right? We're going to cache those in the CPU today. And then we're going to spend a whole bunch of time on the CPU running the IO filter pipeline and data type conversions on the CPU to decompress those and type convert them and bring them out into the form that the GPU eventually needs. And then we're going to transfer the uncompressed version, bigger, takes longer, from the CPU over to the GPU. And then finally, the GPU can go do something. But all the while, the GPU is just sitting here, right? The CPU, relatively speaking, much slower, is doing all the work, and the data comes in, gets transferred over the interconnect, once uncompressed and once compressed, right? That's assumed 2x compression, right? It's 3 times as much memory going over the interconnect as it could be, right? Once for compressed and a double-sized uncompressed version coming over the interconnect. So we're chewing up lots of time. We want to make this different, right? Where we need to go, and I'm going to keep calling them GPUs. They're accelerators. It's fine. Intel, AMD, whatever. It's all cool. It's just shorter to put on my slides than accelerator all the time, okay? Where we need to go is something like the I/O is performed with, in NVIDIA technology, a GPU direct storage call. This will be agnostic. There's HIP, and there's all kinds of good things from AMD and other places. This will be pluggable. We need to get the data sets to be cached in the GPU memory, accelerator memory. The I/O filters have to go actually execute on the GPU because they're wicked fast, including the hardware decompression engines that are built into modern NVIDIA GPUs that go faster than a memcopy. It's literally faster than a memcopy to decompress gzip data. And then we don't need to do any more transfers, right? It's already on the GPU. What that looks like instead is say, hey, the GPU needs some data. CPU kicks things off with something like GPU direct storage, coup file in NVIDIA or whatever, AMD's HIP file or something like that. Decompressed data moves once. I'm sorry, the compressed data moves once over the interconnect and goes and sits in the GPU memory directly, right? So we've minimized our use of the interconnect. It's already in the GPU. Now the GPU kicks in and it can start invoking hardware, GPU kernels, whatever, and all the memory is staying local on the GPU, right? So the work happens in the GPU and the memory stays there. We don't get onto the interconnect any longer. And we're done, right? All this magic happened on the fast component in the fast memory with the minimum amount of time on the interconnect instead of all the other ways that we were trying to do this before. So I can't see any questions, but this is a good place. Any questions here? So that's what it looks like today.
The question
we're going to go to. Sorry, what? Hey, Mark.
Hi. So would you imagine that this GPU decompression would be part of the HDF5 library, or are we going to just use kind of direct chunk access to facilitate this?
I will get there, but it will be pluggable because it has to be pluggable in order to be vendor neutral, right? That's where we have to stay. It's an important and really important part of HDF5.
Great.
But I'll get there. Anybody else?
Nothing in the room.
No.
Go ahead.
Okay, cool. All right, so that's what we had today. Showed this. So once again, we worked really, really hard to make this everything in HDF5 much more transparent, much easier for the apps to move and migrate and update. So we won't need to change, right? Because we can do the DLL stuff and do dynamic loading like we do for vols and say, hey, we'll just go grab that and link in the dynamic library for you. And then we auto detect the buffer pointers and say, oh, you gave me a GPU buffer. That's awesome. I will compose the correct IO pipeline out of the components that I have today, pull the plugins from DLLs or, pre-specified if the app has already linked them in, whatever, and build the best pipeline I can. Doesn't always probably going to be able to run on the GPU, right? It's going to take a little while to migrate things up and over into that architecture. So sometimes we're going to have to compose the pipeline and move data back and forth. Hopefully not back and forth, but just once. between the GPU and the host. But this should be transparent. Again, apps won't need to change their code. They can just do the normal, specify the environment variables, and we'll bring in the right DLLs at runtime. Now, this is kind of where Mark was going. Architecturally, this is what today looks like. I'll walk it through a little bit. So when the app, at the very top, calls dataset write, we got to decide, hey, is this chunked or contiguous, right? But the very first thing we drop into is this gather scatter loop where we're pulling data out of application memory and we're deciding where does that need to go, right? We're going to scatter it out into storage eventually. And today, that involves a type conversion that's embedded in the middle of that gather scatter loop. It's just historical. But when you back out a little bit, you can think about that type conversion. It's just another transform. It's just a byte swap, or we're doing floats to ints or something else like that. It could easily be thought of as a step in the I/O pipeline that the chunks use. So the chunks fall out of this. They do the type conversion over here, and then they get their data set into the cache. And when things get evicted from the chunk cache, it passes through the I/O pipeline where compression and other stuff happens today. And then eventually everybody goes to disk, whether you went down the contiguous side of the world where only type conversion happened, or you went through type conversion and then over into the chunk cache and evicted with transforms. Sure, fine, we get to disk, right? But today, the only path that is possible with the GPU Direct Storage driver, the GDS driver, for NVIDIA hardware, but pluggable for anything, right? Anyone could make another VFD that used HIP or something else. The only one that works, the only path that works, is the pure zero copy path. Yes, it can be gather scattered, but no type conversion can occur. It only works for contiguous data because these allocations that we do today to allocate memory all happen on the host, right? They all happen on the CPU. So that's not going to work when we've got a GPU buffer unless we understand that that GPU buffer has to move, or we've got to change our memory allocations to be on the GPU itself, because the orange boxes don't understand what GPUs or accelerators are either. They think they're operating in host memory all the time, which is why the memory has to get allocated on the host today. So this blocks off chunking in entirety, right? And anything that involves type conversion today for contiguous data sets and all the other kinds of layouts we do, right? So we've got to fix this. This is where we need to go change. So fine, I'm going to walk this too, but much, much simpler architecture. We can do this so much simpler. We're going to move, well, I'll walk it through. Same thing, data set comes in from the application, it's chunked or contiguous. We go drop into our gather scatter loop because we got no choice, right? We got to pull the memory out of the application's, we got to pull the data out of the application's memory somehow. And then we got to eventually get it out to disk. So we got to do the gather and the scatter somehow. But instead of putting it into a chunk cache that's on the host, we expand the chunk caching algorithms so that it understands it can have chunks that are cached on the GPU. So right? We're going to allocate memory that could be on either the host or the accelerator for the chunk cache. Make the chunk cache smarter about where it's located. Then we've got to expand the I/O pipeline, right? We've got to move the allocation again, right? So that it can allocate memory that's either on the GPU or on the host, so that it can do transforms and compression and conversions that occur in either place, right? We've got to be able to compose these pipelines. And we got to move eventually, over time, our I/O filters to be at least capable of running on the GPU. We got to move our data type conversions over time to be capable of running on the GPU. And because we're moving data back and forth, we need a new kind of filter, if you will, a transfer filter that the pipeline composer inside HDF5 can use to say, oh, this is a no-op transfer filter, but what it does is it moves data between some host memory and some GPU memory so that I can finish composing the rest of the pipeline with the correct set of filters in an optimal way. So we're going to move a new kind of filter into the pipeline. But fundamentally, we get the data type conversions out of the separateness that they have today, and we unify them with I/O filters to bring them all together. Then everything gets so much easier, right? It looks like the other pathway that I was describing before. Eventually, everything gets out to the file, but we've made the architecture so much simpler, at least conceptually. There's a lot of work here, but still. By making all four of these places be GPU aware. The writing to the file has to have like GDS drivers, a VFD that understands how to do direct transfers from a GPU over to some network, some storage that's attached to the interconnect, right? Coup file today, HIP file, or whatever AMD's is. We've got to make the allocations smarter so they understand that, hey, there's at least two, maybe more types of memory that we can allocate to, store data within. And we've got to update the filter pipeline to really be a single unified mechanism for transforming data in and out of the file. Big picture, flowcharty level, this is where we're at. Does that answer your question, Mark?
Yeah, somewhat. I guess I'm thinking also just in terms of other accelerators, SIMD and
Yeah.
multiprocessor systems. So I'm wondering, I mean, is the IO pipeline in HDF5 currently parallel capable, and how would we enable parallelism on the accelerator?
Right now, today, well, Neil did the prototype of this like 10 or 15 years ago, where we built a filter that understood the like multi-threading internal to the filter. So you got a chunk of data, and then it decided, oh, hey, I'm going to spawn 16 threads, right? And I'm going to go do an embarrassingly parallel operation on this buffer. But it was within the filter itself. And I think that's still very possible. Obviously, it's still valid because we did it 10 or 15 years ago. I think it's a good idea, but I got to get here first, and then we can think about making, more parallelism within the pipeline. I think it's a great idea. And multi-threading things will certainly enable that capability now that we're actually getting to that point in HDF5. So it's a good point. I will write that down. Hi, Elena.
Hi, Quincy. So well, the question is it you designing this or you start implementing this?
I have not yet begun implementing this because these are going to be fall interns.
Okay, so let's talk about, I think you and John, because we're designing a new chunk cache, and I believe contiguous data sets also going through the shared chunk cache that will be multi-threaded and will allow what Mark is asking to do. So we definitely didn't have a chance to look at the accelerator, so our focus is on shared chunk cache, sparse data, and variable length data. But this is something, if we want to contribute to HDF5, definitely should be,
Yes, that's been sitting in the back of my mind thinking, I'm watching Neil do this chunk update.
Right, an effort, and a shared chunk cache should be, because we cannot now with the data sets we have chunk cache for per data set. It's too much memory.
Oh yeah, right. No, I totally agree with you. And it is in my plans. It just didn't awesomely fit in the talk. So also design wise, if we get into this a little bit more, right? I'm close on time. It'll be okay. here's at least some of the places that I see we need to change in HDF5. There's going to be a few more probably because, there's always new things that pop up. We've got to update the virtual file driver interface. So we're going to have to bump the version on many of these things, right? Anything says update. The VFDs, at least the library has to know whether the VFD could do I/O from a GPU or accelerator buffer, right? It can't just give it a GPU buffer and then say go and then segfault, right? That's not. So it's got to be at least able to think about whether this VFD can do what it wants it to do. We've got to add that the memory allocator, so that the library understands that, oh, I need a memory buffer that's on the accelerator, or no, a host buffer is fine. But we've got to make that pluggable again so that both, all the hardware vendors can come in and say, here's a HIP buffer, here's a CUDA buffer, whatever. This is the chunk cache that Elena just was talking about. We've got to, expand this so that we understand where the chunk caching goes. That's going to be a little different. It doesn't have to operate any particularly different. I think it's kind of a localized change in the chunk cache itself. It just has to say, well, this is a buffer that's over there, not over here. Everything else is pretty straightforward. Obviously, the filter, as the most bullets, is probably going to be the most impactful and difficult to get done. We've got to at least update the interface to filters so that you know where the buffer is, right? Can you operate on a GPU buffer, or no, your filter only runs on host in CPU computation? You got to add these kind of transfer filters, which are straightforward, just like memcopy, CUDA memcopy between a GPU buffer and a host buffer. No big deal. In order to move the data type conversions in, we've got to at least add a little wrapper around them to make them look like a filter. I think that could be more efficient, but let's get this off the ground, right? Get the wrapper around data type conversions so that we can get them into the I/O pipeline. And, backward compatibility for existing filters. They'll get default flags that say, I only operate on the CPU, and I need buffers that are in the CPU, but we can bring them in and just put a little shim around them that says, fine, I know what you're going to do here, and you're going to only operate on that piece, and that's how the pipeline will think about it. And again, type conversions are going to be similar. There are occasional rare users who have implemented user level type conversions that they register with a library. So we got to make certain that those continue to work. But again, no big deal because we have to do that for our internal filters. Type conversions as well. And finally, what I think the benefit's going to be, and this is kind of a combo slide, but I think with multi-threading, actually I think it's going to be better than 4, but I'm trying to be a little conservative. It's kind of like number of cores, better, multiple for reading. Sharded storage I'll talk about tomorrow, just happen to have it here on the slide. For this accelerator-native stuff, I think at least GDS or something like that for vendor-neutral platforms is going to boost our performance by at least 2, and I'm kind of hoping 3x better I/O performance. We're going to need to rework some of the page cache, and when we're also, which gives us a boost, and then also just doing the data directly to and from the GPU allows a host memory transfer out of the middle of that to make it faster. I can today compress data with the NVComp, the NVIDIA compression library that's built with GPU kernels and leverages the hardware, and easily see multi-x decompression performance speedups today. How much of that is your whole entire pipeline that we're talking about? That's where I can't tell what the overall benefit is, but it is a lot faster on the GPU. And the type conversion, again, you can do this at basically memcopy speeds in a GPU kernel. And so this should be radically faster again on a good threaded CUDA HIP kernel. So I think our performance improvements are going to, at least with compressed or type converted data, are going to be close to an order of magnitude improvement for today's I/O pipeline. Moving off the CPU and on to the GPU, we should dramatically reduce application time, 30 seconds down to 3, roughly. Let's think about it that way. So I've got a couple of follow-ups that are like, hey, what if we had TPUs and Bluefield devices and things like that? But does anyone have any thoughts or questions here? This is probably a decent place to kind of pause and keep us on time.
So, what I'm thinking about is, it seems to me that the optimal use for this would involve larger chunks.
Yeah,
Right. And basically, if I gave, if I had 2 GB chunks that were maybe subpartitioned as a shard, and maybe you'll talk about that tomorrow, or as I just mentioned, and then this would allow the GPU to then, in parallel, decode those chunks, and load that into then another larger buffer to get back to
yeah, sure.
the library. But I guess that makes me worried a little bit because now I'm making HDF5 files that have smaller chunks optimized for traditional pipelines and larger chunks optimized for these kind of things. And I'm wondering how to resolve that.
I think the way to resolve it, at least the first solution that comes to my mind is, well, let's leverage our asynchrony, right? So even if you feed me a whole series of smaller ones, if I can pipeline them in the background or out, that solves an awful lot of problems, given enough memory. But I think that's the first cut, I would say, right? Because you're right, a bigger buffer is going to be much. The GPUs are getting a lot better about the chunkiness of the things, and they work much better with smaller stuff today than they have historically, but it is still a factor.
I think Martin had his hand up.
Yeah, Quincy, thanks for your interesting talk.
Sure.
Two type of questions, actually probably not too much related to another. First, more general question. Are there any, let's say, rules of thumb available concerning the overhead the current HDF5 practices implies when we talk about conversion and scatter-gather operations? Because it's a long-term, let's say, a multi-decade discussion within the physics community actually to go for a, let's say, similar representation of your data in persistent storage or in memory to avoid any penalties in moving it from storage to memory and vice versa. And for that, I try to figure out, are we able to, let's say, get some sort of basic good enough assumptions of what the overhead today is? And the second question is, would it be also the goal for this activity to include FPGA cards as an accelerator and including cards which have their own, let's say, RDMA capable network interface? So where the accelerator not only has its own memory, but it also has its own network card.
Sure. I think that would be kind of a combo VFD. You probably have to just write 2 separate chunks of software, even if it was still the same piece of hardware underneath. A VFD that understood that it's doing direct transfers to its NIC from the GPU, from the accelerator, and then pieces of software that operated directly on the accelerator itself in order to do the computation pieces of it. Underneath, yes. I mean, even NVIDIA cards have these kind of things today. So
yeah,
I'm just kind of orthogonalizing them in the software there.
Okay.
Benefit wise, I mean, today is today, right? I mean, we can measure and benchmark and do what we're doing. And I was attempting to make some estimates about what the future could look like for these things. But then the hardware changes and how well do we do this and things like that. I think overall my thought would be to say, well, no, I have to go back to me slide. Okay. We will try to make it as transparent as possible and tune, right? To make it say, oh, look, there's this case that we're not covering well. Let's update the pipeline so that it understands that that case exists and it can work properly and adapt to the circumstances that go there. Elena will probably remember this. Mark Miller asked me 20 years ago, go do a transform library. And we're finally getting there, right? We're finally getting to the point where it's both valuable and we have the software capabilities built up enough that we can actually compose arbitrary pipelines to do our data transforms on the fly. And I was trying to cover the FPGA piece of this by saying possibly other memory, right? So it doesn't, it's going to be vendor neutral. You could write a driver that works towards anything, towards any piece of hardware that you came up with. I think that was most of the questions.
In some of the later slides, you mentioned explicitly CUDA and NV something.
Sure.
Which, of course, NVIDIA specific. Okay.
Yeah, I mean, that's just the easiest words for me to drop in here.
Sure.
I can't keep making ///////, but yes, it will be vendor neutral.
Okay.
And I don't know what the performance will be on AMD hardware either, right? So
no doubt, no doubt. And any let's say simple rules to estimate the overhead today in this conversion and these chunky memory layouts where you can't do massive.
We try to be really efficient
accelerated.
today. Mark's talked to it. We do try to be really efficient today, but since the hardware is so much faster, we can get these kind of improvements when we move to faster hardware. That's fundamentally what we're benefiting from here. Our software is pretty good. Modulo bugs, modulo some inefficiencies, but we try hard.
Okay, thank you.
Yeah, sure.
Okay, I think we'll continue the discussion maybe at the roundtable later in the day. So let's thank our speaker once.
Yeah.
And we will resume at 20 after the hour. So thank you.
So Quincy, question. In your picture, so we have now, or theoretically, right, at least prototype to read data directly to GPU, right? And
yeah, the GDS driver works.
Right. Yes. And then compression, decompression will be there, and of course filters can be improved to use to take advantage and use multi-threading and so on. So do you have a really use case when you have to move data from CPU to GPU instead of just okay, if you want to use GPUs, read directly, or it's restricted by memory? Why such a complex picture of communicating with CPUs?
Well, there's a long-term evolution in the code bases for applications and the workflows. Some of them are still very much based on CPUs, strangely. Right. Even the NVIDIA ones, we're like, okay, you're only using this GPU kernel in this one little place, but fine. So I got to be able to at least move the data back and forth because I can't always guarantee which way it's going to look. So that's why I ended up adding in those transfer filters into the pipeline so that when necessary, the pipeline can build one in. But ideally, everything sits in the GPU for as long as possible, and it never touches the host.
So it's kind of, I don't know, maybe stupid idea, but why can't we duplicate the caches on GPU and CPU? And if buffers on CPU, you do it from CPU. But it's separate, so you separate concerns.
Oh yeah, totally. The cache has to know on a buffer, on a chunk by chunk basis, is this chunk buffer, is this cached chunk in host memory or in the GPU's memory? It's not a global decision, Right. I know most application, I can't imagine a good application partially dividing a data set between the.
That's what, that's what I'm kind of, it will be good to have really talk to apps and find use cases just to help with design. Because it will work. Okay.
It just has to happen because, particularly, I didn't get into it in these doc. The parallel side of the world is even slower getting to GPUs, right? So MPI doesn't understand GPUs as well as other things could. Right. And so sometimes if you really feel like the benefit from collective IO is going to work for your application, you're still going to need to pull the data off the GPU into CPU memory and do the IO as a collective IO somehow.
Right.
So I got to have the movement as part of the pipeline as well.
And one more quick question, Quincy.
Oh, sure.
So, I was just wondering how your scheme fits into the unified memory concept.
It's just another type of memory, right? So as the world evolves into a unified memory, maybe we get to a point again where it really is all one kind of memory again. And this was a transient phase in computing where there were two separate pools of memory, attached to different kinds of compute hardware, CPUs and GPUs, and we get back to a unified pool of memory. Maybe, I don't know, but it would work. It just, it would make a little bit of the work that I'm talking about here kind of moot.
Yeah. I guess what I'm wondering about is you kind of mentioned auto detection of the type of memory. But I'm wondering if it really should be like responsibility of the caller to say, no, I really need a zero copy pipeline here. Here's a pointer. Don't worry about what it is. I know what it is,
Yeah, I mean, if we want like something like the chunk direct IO stuff, sure, but you're playing pretty fast and loose there. You better be right.
Well, at least it should be an option.
Sure, it's fine. Live dangerously. Take all the guardrails off.
For all users who can use all these new devices and memory, they definitely know what they're doing. Otherwise, they will be.
Yeah, and I don't think it's going to be overall beneficial in a large way because detecting the buffer type is trivial, right? It's just a little function call. It says, what type is this pointer? Oh, okay, that's a GPU. Okay, I'll go build a pipeline that involves a GPU-centric filters. Fine.
Yeah, but you have to build interface, right? So you can, with different GPUs, it's probably different APIs.
Oh yeah, that's part of the pluggable memory thing that I was working on designing there. You got to do the allocation, you got to do the detection of which buffer is, and it's all got to be abstracted in some little function pointer interface.
So in general, I think in HDF5 library, you have to design through this abstract interface and not worry about. Then, yeah. And the same with designing caches. Yeah. Okay.
Yeah. Right. Yeah.
Yeah,
this doesn't look hard. I'm not doing difficult engineering. It's just a lot of like rearranging where the pipes go.
It's retrofitting, and the approach we're taking right now with this new cache, we're making it kind of coexist with what we have now and then maybe switch in the future. So I do the
scaffolding all the time too.
Okay.
Yeah.
One of the things I find interesting about some of the newer languages, Rust, Zig, is they have a little bit more explicit interfaces to control memory allocators.
Yeah, I like Rust.
And yeah, I'm trying to think about how that would play into this, because maybe we have something that's an allocator that in some ways is also kind of more copy aware as well, that it wouldn't copy as much as if possible, or I don't know. I'm not really, haven't.
Unless we start re-implementing, the guts of up into the guts of HDF5 in Rust, I got to pass through that abstraction layer anyway.
Right.
And fine, if you want to write your plugin in Rust, great, it's cool. I've done that.
To some degree, I do think when Zig matures, that might be a slightly better match, just because it very much does keep to the C kind of paradigms, but
I'm not that familiar with Zig.
Just a little bit tighter about it, but it's just a little bit too immature at the moment. But it does feel like more like an enhanced, slightly more memory safe C than Rust, which seems to be something completely different in terms of how do you think about a program, right?
Yeah, no, I agree with all that. But like I say, until we get into let's go rewrite 500,000 lines of code and something else, or at least a chunk at a time.
We should ask AI to do this.
Sure. I've tried to wrestle with the AI, and it's helpful. It is helpful, but it is nowhere close to able to do this.
You know my C programming skill, right? So when I was preparing for demo, it would not compile, and it was spitting on me a lot of error messages, like the stupid C compiler telling me something I even do not want to know. So I asked ChatGPT, and essentially I was surprised. ChatGPT gave me some nonsense answers which were good, so very nice rewritten program, etc. And that was not what compiler was barking at, but it gave me an idea what I should look for. So I
Okay.
have to comment just one line. That's so then compilation went. So, but it was very useful.
Yeah, well, I use some of the AI tools for programming, and like I say, they are useful, but nowhere close to perfect.
There is not ChatGPT. Someone told me about another one. I forgot the name, Claudia or something.
There's a
They're
ton.
much better in at least creating different scripts and especially Python scripts. And
Yeah. Well, if you want to create a calculator on the web, they're really good at that. But anything that involves something complex,
thank you, Cursor. Yeah. But I was amazed. Like it really helps. So otherwise, I would not be able to prepare.
Well, I think just about almost every other day there's a new model. So um, I'm still trying to parse out the Google I/O dump the other day. So
Mhm.
Quincy, is part of this work actually motivated or supported or in partnership with the, let's say, the LCLS data processing activity you're
I
historically
do
been
talk to
involved in?
Slack quite a bit, and they would like to have this. Yes,
Okay, okay, got it.
I have several meetings a week.
Okay, good to know.
All right, looks like you got it, Scott. I'm gonna go have a holiday.
yeah, see you tomorrow, Quincy.
All right, bye guys.
Bye bye.
Yeah, Mark, I look at those, file formats. They really easily map to HDF5, so writing wall connector should not be difficult.
Yeah, should not be difficult.
Yeah, it just needs to be done.
Yeah, as you say, I just have to brush up on my C skills a little bit and maybe just get into it.
We actually submitted grant to write with Ed for NetCDF to write those wall connectors for HDF5 to use with GeoTIFF and ZAR and others. So maybe we'll be funded and we'll be able to write it. We'll see. But I will pursue in that direction because it's really now such a powerful mechanism with VFDs involved because you really do not need to change the library. You can work on the top level or low level to access data.
Absolutely.
Mm-hmm. So Scott, how is coffee?
It's good.
Good. Okay, good. Are there any pastries there?
Yeah, some
Ah,
cookies.
cookies. Okay, good. So Igor helped. Igor helped. Did you have a chance to see Hamburg?
No, not yet.
Hmm. I'm just so upset that I couldn't go, just.
Okay.
how is the room? It said there is no camera that shows you the audience.
There was a camera, but I think it's turned off now.
Oh,
or
I
it's not.
see.
It didn't really show the screen, so it wasn't all that helpful.
Mm-hmm.
I mean, you can turn it.
Oh, yeah.
Mm-hmm. But it cuts off the screen, so it's
Oh, I see. Yeah,
you
yeah.
point at it and you can't really see anything.
Right. But for roundtable, it will be turned on, right?
But
For roundtable, it will be turned on.
yeah,
Okay.
I'll leave it on. I'll leave it on. It doesn't.
But if it's interfered, it's okay. Just use whatever is more convenient.
Mm-hmm. Huh. Guess I'll have to call people back in.
It's a long day. Mark, are you on East Coast?
Yep, I'm near Washington, D.C.
I see. It's a little bit easy for you, 1 hour closer.
But get started. Get started. Is the sound all right? That sounds good.
Yes.
Okay. Yeah. Give a few minutes for people to come back in. Well, I guess we'll just get started. Maybe people wander in and start talking. So I'm Scott Breitenfeld from the HDF group, and today I'm going to discuss powering the future with data. So what's now, what's new, and what's next with HDF? Hold on.